Let's welcome Dr. Chen.
Thank you. First, I would like to thank Professor Xu and Minghui for the invitation. And I'm also very pleased to see Phil being here, because I mentioned to you yesterday, both my talks are somewhat related to you. So I'm so glad that you're here. So the first part of my talk is on aviation impacts on climate. And this is future projection in 2050. So here's just an overview. This is aviation in 2005. This is taken from AR4. And I'll just focus on aviation aerosols, the sulfate aerosols. Based on this assessment, the global impact is about 4.5 watts per meter square minus. It has a slight cooling effect. And aviation soot, black carbon, has a slight warming effect, being 3.4 milliwatts. And for linear contrails, that's the contrails you can identify being really fresh in the air. And the assessment is 12. Based on the CAM5 simulation, we've got something like 3 to 4. So definitely on the lower end of this estimate. And due to spreading shading in the atmosphere, the contrail will become distinguishable from cirrus, called cirrus contrails. And based on this assessment, it is 33 milliwatts per meter square. And our assessment based on the 2006 aviation emissions is about 13. So again, CAM5 falls on the lower end of the estimate. Or people will typically ask me about why do you care when the impact is so small. I'll point out, based on aviation emission for the carbon dioxide emission, the forcing is about 28 milliwatts, which is on par with contrail cirrus. If we are concerned with carbon dioxide, we should be concerned with contrail cirrus as well. Like I said, the focus is on future, the 2050 emissions. And so we use CAM5, and we got this aviation emissions inventories from the FAA. And there are 4 scenarios based on whatever population projection, economic growth projection. They come up with a so-called baseline emission. And the second emission, so-called scenario 1, it assumes from now on, per year, you gain 2% increasing engine efficiency. So you are going to burn less fuel, flying the same flight distance globally. And the third scenario, they say we have further improvement with our engine, then you cut all the sulfate emissions, and you reduce the black carbon emission by 50%. And the last minute, they added another scenario, scenario 3, basically the same as scenario 2, but there's a 5% increase in water vapor. I'll just say it now. It makes almost no difference whatsoever, but we have to do it. And so the inventory, the emission species considered in this talk are water vapor and sulfate and black carbon emissions only. And since the impact, based on our previous study, we know the impact is so small, so the configuration of the model is the so-called specified dynamics, which will reduce the internal variability of the model so we can pick out the signal of aviation impact better. And the background meteorology is taken from a previously performed fully coupled simulation based on RCP 4.5 and 8.5. And we use 4 slightly different annual meteorology to address the uncertainty based on different background meteorologies. So here's the fuel burn or emission. In the future, the horizontal axis is year from 2006 up to 2050, and the vertical axis is ratio against the current level at 2006, basically. I'll point out for the 4 solid lines are flight distance. The black is global flight distance. So based on the projection, the global flight distance will increase by a factor of 4 by 2050, which happens to be the same as the flight distance in Central Europe. I don't know how they got into this conclusion, but this is what it is. And the red solid line is the flight distance in eastern US. Fairly surprisingly, it actually projects a factor of 2.5 increase by 2050. And the biggest growth is actually in here, in East Asia. It projects to grow by a factor of more than 6. So also plotted here is fuel burn. So you get two scenarios. I plotted the baseline and the scenario 1, the 2% engine efficiency increase. So basically, for example, for East Asia, you get two lines on top. This is the baseline fuel burn. This is scenario 1. So when you get this engine efficiency growth, you can fly the same amount of distance, but you burn less fuel. And all emission species are basically scaled linearly with fuel burn. So this basically represents how much aviation aerosols will be emitted based on the scenarios. So this is actually taken 18 months ago when I came to this workshop, taken at the Mesa Lab at NCAR. In March, that's when you see a lot of contrails over your head there. So this will be called the linear contrail when you can identify that. So basically, I mentioned this. There are two conditions. When two conditions are being met, then you probably will have a good chance in seeing contrails over your head. That is, of course, first you need to have a fly over your head. Otherwise, you never see a contrail. Second is, at a given altitude, temperature has to drop below a critical temperature, meaning the temperature has to be low enough. And also the air has to be moist enough. Otherwise, the water vapor emission from the aircraft will just evaporate. And now we call that, when the two conditions are met, we call that persistent contrail condition. And here's just plotting. The top panels are the temperature in the mid-latitudes in the northern hemisphere. So the black line is the current condition, and the RCP 4.5 is the red. RCP 8.5 is the blue. It's basically showing in the future, in 2050, based on RCP 8.5, temperature will be warmer, so the frequency for the two conditions being made will be lower, so you get less contrails if you use the future background meteorology based on RCP 8.5. Basically, that's what this top panels are showing. And this is the frequency of persistent contrails at the cruise altitude at about 2070 hectopascal. So basically showing in the mid-latitude and polar region, it is almost, the two conditions are met almost 100%. And in the tropics, temperature being higher, so it's less. And the two panels on the right are the difference from the current time for in 2050 based on RCP 4.5 and 8.5. So here is showing you have a further reduction for this frequency based on RCP 8.5. So if you use the background meteorology from RCP 8.5, you get less contrails. Basically, that's what's shown here. Here's actually the final result. The horizontal axis is year. This is the radiative forcing based on contrail series only. Basically, we only consider water vapor emission in the simulation. So I would just focus on, first of all, since all the curves are so close together, so immediately you know by enhancing the efficiency of engine, it's not going to do anything in terms of contrail series radiative forcing. But the background meteorology does matter. I'll point out the three red lines. The top one is the dashed red lines based on the future aviation water emission on top of current present-day meteorology. So you'll be getting the highest radiative forcing. If you use RCP 8.5, that's the dashed dotted red line. It's a bit lower. the solid red line is based on the background meteorology from RCP 8.5. And again, the reason being the background meteorology is the warmest based on RCP 8.5. The middle panel includes all emissions, including sulfate and black carbon. I'll just jump to the end because if you take the difference between the top two, the first two panels, you would get the so-called deduced aviation impact. So you get this cooling effect due to aviation emissions. And I'll just point out this is due to sulfates. And these scenarios are scenario 2 and 3 where you don't have any sulfate emissions. So you only get aviation soot. It has a slight warming effect, but it's almost negligible. And when you go to scenario 1, you burn less fuel, so you actually emit less aviation sulfates. So the cooling is slightly less too. So here's the zonal average plot. I will look at the green being the simulation with only aviation water vapor in 2050 based on the baseline scenario. The blue also includes aviation soot and aviation sulfates. So here's the panel of shortwave cloud forcing. The green in the mid-latitude, basically you are looking at the signature of Contour Cirrus. It has a slightly cooling effect, but the long wave overwhelms the short wave, so the net effect for Contour Cirrus is positive. But when you also include aviation aerosols, both the long wave and the short wave cloud forcing are enhanced. The net effect is mostly cooling in the lower latitudes, but in the mid-latitude you still get the signature of the Contour Cirrus. And if we look at, say, liquid cloud water path difference, if you don't include aviation aerosols, you are not going to change the liquid water path. However, when you include aviation aerosols, you're going to enhance liquid water, basically warm cloud. I will just say now, because I don't have much time, this is due to aviation sulfates. And when you move to the ice water path, there's enhancement of ice water path. For the green, that's the signature of Contour Cirrus. But when you also include water, aviation aerosols, the ice clouds are further enhanced. That's due to aviation soot. So here are just the the aviation so-called all emissions. Water vapor including also aviation aerosols. The black is the 2006 level, the red being the baseline in 2050, the green being the 2050 scenario 1, assuming a 2% increase in engine efficiency. The blue being scenario 2, same as scenario 1, but you lose all sulfate emissions. So we'll just jump to liquid water path difference. So you can see the blue, you almost lose that enhancement of warm clouds. And for the ice clouds, all three scenarios in 2050 show similar enhancement in the ice clouds. That's due to aviation sulfates, aviation soot. So this is the regional impacts. The top panels are based on the 2006 emission. Panels on the right only include water vapor emission. In 2006, locally, we're looking at about 0.5 watts per meter square in Central Europe. But when you move to 2050, we're looking at about 2 watts per meter square. When you include aviation aerosols, you reduce the warming over Central Europe or Eastern US a little bit, but the key signature is actually you see negative forcing over the ocean mostly, and they happen to be in line with the flight corridors. In 2050, the forcing is larger, but the signature is almost the same. Basically, the negative forcing is over the ocean mostly.
And can I just confirm, is the
for everything. I think it's mostly for the low clouds, but yeah. So just zoom in to what I just showed earlier. The panels on the left are just contour series. Panels on the right also includes aviation aerosols. You see the negative forcings over the ocean, but it actually also reduces the positive forcing due to contour series. So here is just a histogram plot. This is the global radiative forcing due to different scenarios. I'll just point out the first bar is based on the 2006 water vapor emission. The 2006 contour series has a big jump if you jump to 2050 emission. I'll just point out the biggest jump is in East Asia. The ratio is about a factor of 7 or 8. And the bars on the right also includes aviation aerosols. I'll just point out quickly, globally you see this net negative forcing, but when you look at Eastern US, Central Europe, the net forcing is still positive, again, because the negative forcing falls on over the ocean. I'll skip this. So I'll look at the ice liquid water path for now. JJA on the left, DJF on the right. The top panels are just contour series. This is the 2050 condition, the baseline emission. When you take the difference, you see the ice clouds being enhanced, mostly in the high latitudes in the Arctic. This is due to aviation soot. And this is the liquid water path. The top panels are taken from the background meteorology from RCP 8.5. And the bottom panel is the difference due to aviation aerosols from the control simulation in which there's no aviation emissions. So when I saw this plot pop out on my screen, I almost screamed. But I presented this in my section last week. No one knew why I was screaming, and I tried to give them hints and hints. No one could get it, so I just point out why. The increase is where where the background liquid water path is high, or there's flight over your head. For example, you know this is a flight corridor between North America and Asia. And this is the flight corridor between North America and Europe. You get this increasing liquid water path. And this enhancement is because there's a lot of emission in Central Europe. Again, here, the same thing in Central Europe, and this is the flight corridor between Asia and North America, because there's a lot of emission due to aviation emission. And there's a lot of similarity if you just look close enough. Here's the background cloud, basically, and this is your enhancement. There's some similarity between the background and the delta liquid water path. So why is that? So I look at the short wave forcing. This is just due to aviation aerosols. So we have two sets of experiments. One was only aviation water vapor. The other is aviation water vapor plus aviation aerosols. When you take the difference, basically you're looking at the impact of aviation aerosols only. The top panel is the delta short wave at the top of the atmosphere. So this is basically due to the liquid water path increase. The long wave, the positive forcing, is due to the enhancement of ice clouds. And this is the difference. The net, long wave plus short wave. So when I take a cross section at 40 degrees north, this is the aerosol concentration. Acamol is basically the smallest particle. All aviation sulfates will get into the acamol, and aviation soot will get into the prime carbon mode. By the way, I used the most comprehensive aerosol model in chem available. That's the MEM7. And this is the accumulation mode. both aqueous mode and prime carbon mode can be coagulated to the accumulation mode, which is the being most effective, serving as ice nuclei. I'll just look at, this is the background accumulation mode. This is at 40 degrees north. So this part is basically Europe, then Asia. This is North Pacific, North America, and North Atlantic. And so you see over this two ocean gyre, the aerosol concentration is less. Is to be understood. And this is the difference when you include aviation aerosols. By the way, this is a log plot. So when you when you include aviation aerosols, even the accumulation mode is enhanced. This must be due to aviation aerosols, because we were looking at the increase mostly at the cruise altitude, but no, actually there's enhancement of accumulation mode even at the Earth's surface. This is the aqueous mode. Basically, you're looking at the increase by aviation soot. And this is black carbon. The background field doesn't have black carbon mode. So that tells me the aviation aerosols must be brought down by the circulation of the atmosphere. So there's increasing the aerosol number concentration due to aviation aerosols. So next I'll look at the cloud drop number concentration. The top panel is the background at the same cross section. And you have the baseline simulation, scenario 1, scenario 2. You get the enhancement where you have mid and low level clouds. This is over North Pacific. This is over North Atlantic. We're looking at about 10% increase, which is almost in line with the increasing background aerosol concentration. But when you move to scenario 2, you don't get the same kind of increase in cloud drop number concentration, because in scenario 2, there's no sulfate emissions. And also look at the cloud liquid mixing ratio. Again, the top panel is the background, the baseline, and scenario 1 and 2. This is delta. It really puzzled me why the cloud mixing ratio increased, because I could understand when the aerosol concentration is increased, then you get more drops. But I don't see how the cloud liquid mixing ratio increase. So it kind of puzzles me a little bit. Then I look at this final plot. The top panel is the percentage increase in cloud liquid mixing ratio, JJA and DJF. And the bottom panel is basically the lifetime of clouds. We have a frequency kind of factor in the model, which will tell you how frequent, how persistent the clouds are in the model. And they give you a fairly striking similarity, at least say around 800 millibar. It tells me the mixing ratio, cloud liquid mixing ratio increase I showed earlier was due to the fact that now the clouds being persistent due to the presence of aviation aerosols. So this is a so-called second indirect effect, the Albright effect. The first effect is the Toomey effect when you increase the cloud drop number concentration in the clouds. So both effects are at work. And I happened to work with Phil a few years ago on cloud seeding geoengineering. And we were actually looking at brightening the low clouds by doing this, doing these two effects together. So in the future, when you take a flight, you probably can think of, yourself participating in a geoengineering project. But of course, this is totally unintended. So here's just a summary of my talk. So basically, the take-home message is that when you look at the forcing from contour series, the enhancement of engine efficiency is not going to do anything, basically. And you get the sulfate emissions giving you a negative forcing. And the black carbon from aviation emissions has a slight warming effect, but it also has this cloud seeding effect is also at work by aviation suit. So they kind of cancel each other. That's why the net effect by aviation suit is almost zero. And for this work, since the configuration of the model is CAM, SD, there's no way to address, say, the temperature response to this forcing. Right now, we're looking at our simulation using the fully coupled model. And we do see some significant response in terms of surface temperature. And we also compare the fully coupled simulation with the SUM simulation, and that's under the results are too preliminary, so I'll skip them for now. And I still got some time, so I can jump to my second part of my talk now. Here's the recent development in CAM, but I'll just jump to the very last part of my talk because I'm directly involved in this. And this is very fresh because this just happened about 2 weeks ago. This is actually kind of a saga in the finite volume dicore. There's a vertical remapping. Before I show you this equation, maybe I should just show you the result, final result. This is the result, the temperature profile in the tropics, taken from a Wacom simulation. The black is from the current configuration of the model. So people working in the Wacom group found this kinks. It's pretty horrendous in my opinion. Then I say, well, hold on a second. I had a different remapping algorithm. Why don't you take my algorithm and see what happens? And they did another simulation, that's the red. Which one do you like better? Black? Black? Jesus. It's kind of funny because when I passed the code over, the first person tested it. And suddenly I got tons of email from all the people in the Wacom group. Everyone grabbed the code to do it and then do different simulation and got tons of email. And they got all excited, burning all the gals in NCAR and then show me all the, I was so overwhelmed by their email and basically pointing to the same thing. When you change the vertical remapping, you are going to change this, you are going to remedy this problem. So I'll just give you an overview on what's being done in the finite volume dynamical core. There's a vertical remapping procedure because it uses a floating vertical coordinate. So this is the total energy in the dicore. Basically, the strategy is you calculate total energy in every layer, and then you map total energy and U and V. Then you try to retrieve temperature from the residual in the total energy. That's somewhat counterintuitive, but that's what's being done. And a few years ago, I had a personal conversation with SJ, and he says move to the so-called geopotential remapping without disclosing to me why. But basically, this is geopotential, so it's equal to RD, the gas constant, times virtual temperature, or times d log P, or you can do Cp over potential temperature, d pi being the external function. So you can map temperature over log P or map potential temperature over pi. This algorithm will make sure during the remapping you are not going to change the geopotential at the model top. So I passed basically the third. This, I call it method C. You just map potential temperature directly, and the red is from this methodology. And then I revisit this issue. This is an animation. I will show you, this is the current methodology. This is the so-called method where you map temperature. The bottom panel is when you map potential temperature. Panels on the left are temperature profile. Right is, okay, basically what I set up is I grab a column from the model in the tropics. And I create a slightly different layers. I try to map the potential profile to a slightly different layer, then back and forth in 100 iterations. Since there's no dynamics, you should expect the same thing. You should recover the same thing. And the panel on the right being the temperature difference due to this remapping. Let me show this animation again. Without any dynamics, you can introduce the temperature perturbation up to 60 degrees with the present implementation in the finite volume dynamical core.
Remind us what the middle row and the bottom row is.
B is you just map temperature, and C is you map potential temperature over external function. You've got to love this. You don't need anything. You can create dynamics when there's no dynamics. So we zoom in, to stratosphere and mesosphere, where people are most concerned about in the vacuum community. So why is that? If you remap potential temperature, total energy, you have to remember when you retrieve temperature, you go from the surface and build that to the top. So if you have any kind of truncation error, you pay the price at the model top. That's what's happening. Because you don't care about temperature, you care about total energy. So we look at different configuration. This is CAM 5 with 30 layers. Now, even mapping potential temperature is not going to give you anything better than the total energy and vertical remapping.
So one thing you haven't pointed out is this model has a top
At the bottom.
and the other one has got a top at 150.
Yes. So the test on using vacuum is really tough on this vertical remapping because the potential energy term will get really high when your model top is so high. But there's another factor other than the model top. So B seems to be doing pretty well, but still there's a lot of wiggles there. So recently, Yaga Richter has a 60-layer model where she successfully got QBO. And I grabbed her configuration and repeat the same exercise. It's a challenge to make this plot because you never know how big the temperature perturbation will go. So it just go out of bound at the end. So the 60-layer model, based on this test, none of these approaches will save it. This is about 20 degrees. This is beyond 35. And even more recently, Yaga has a 46-layer model. By raising the model top to 1 hectopascal, also has a much better representation of stratosphere and see what happens. So I think this is doing an okay job. And I zoom in. This is the total energy remapping. So based on all these exercises, I think I can conclude that in order to, not to get this crazy temperature perturbation due to vertical remapping, first of all, you need to move away from total energy remapping because it's just not possible. No matter what you do, it's just not going to save you because, like I said, you pay the price at the model top. If you have any sort of truncation error in terms of retrieving temperature, you pay the price at the model top. And second, you also need good resolution near the model lid. Otherwise, you are not going to save. I can't save it because I have either approaches when you go to this 30-layer model where the vertical resolution is so coarse at the model top, it's terrible. So you need two ingredients. You need to move away from total energy remapping. Second, you need better resolution near the model lid. So that's the last part of this camp development. Since I'm running out of time, I will jump to something people love to gossip about all the time. They will all come to me, so which candidate will win? Okay, here's in preparation of Camp 6, there are two candidates being considered to replace the current shallow and deep convection schemes. That's Club and Unicom. And I'll just show you what they presented recently. Looking at Club here, this is diurnal cycle precept. The top panel is taken from Chen. And this is the peak hour for precipitation, basically. We're looking at, so this is the Camp 5 simulation. As you can see, the precip take place too early when it should be in the evening hour. Camp 5 would dump the precip in the mid-afternoon hours. And in the summer, in North America, Camp 5 is doing the same thing. And this panel is Camp Club with the current deep convection scheme, but I'll jump to the end. When you just use Club to replace also the deep scheme, it shows fairly good improvement compared with Camp 5. Kind of delays the precip. Another candidate, of course, is Unicom. This is OPS. This is Camp 5. I think both Unicom and Club is showing delaying precip. That's something people were concerned about. And also, this is the performance in simulating MJO using Unicom. This is OPS. And this is Camp 5. This is Camp 5 with Unicom. The color shading is precept. Basically, it's showing the precip is just not propagating. But when you move to Unicom, it shows the eastward propagation. So when some parts show me this about a year ago, I feel like, God. But they say it's coupling. It's the coupling. And it's no. If you get the convection correctly, you'll get it. And this is the color shading here. This is just composite for the different phases of MJO. The color shading is OLR. It's very weak in Camp 5, but Unicom is much, much better than Camp 5. And the reason why I don't show the results from Club is because I think Camp Club doesn't really do much in terms of improving the simulation of MJO. And I probably will just stop here. This is the simulation of using a different kind of approach to get MJO in Camp. This is Camp 5 with the same gravity wave drag parameterization that's used in WACM. You barely see any kind of downward propagation, and the zonal wind is pretty weak in the tropics. And I showed earlier this 46-layer model by raising the model top to 1 hectopascal. And then this is so-called the tune version. So by tuning the model, you can get the right frequency of the QBO. So that's a fairly big improvement from the current Camp 5. But unfortunately, I think this configuration is not going to be considered for Camp 6 for whatever reason, because I think they consider the computation will be too much, because we are looking at about 50% increase, jumping from 30 to 46. So I'll stop here and take questions. Thank you.
Question, please.
Can you tell me in the first part of your talk
Yes. The black carbon,
Through a homogeneous mechanism through sulfate aerosols or through heterogeneous?
heterogeneous, through aviation suit. Yeah.
Because the standard model doesn't have soot aerosols being isolated.
Yeah. In this simulation, we assumed 0.1% of the accumulation mode being affected as ice nuclei. Yeah.
And what's the relative amount of, I mean, I was surprised that the sulfate is playing a role in what we call it. So, the conventional wisdom is that there's 65 teragrams of sulfur emissions from surface sources of pollution and another 40 teragrams of natural aerosols.
Mhm.
Or 100 teragrams. So what's the amplitude of the aerosol emissions from aviation?
I would need to check because this is 2050, and with this big jump from the current level, I'll need to look.
I guess I would have imagined that it was so small that it couldn't have any effect at all, but it's very interesting to me that it does.
It actually, from our work based on the 2006 emissions, the year 2006, we're looking at about 40 milliwatts per meter square of cooling due to aviation sulfates. So, well, but that's milliwatts. That's why Cecile has been teasing me as the milliwatt chaser or whatever. Whenever I present this work, she was like, oh, here comes the milliwatt chaser again. Who cares about milliwatts? But I'll point out one thing here. Since I mentioned this, I think it's unfair to call me names. Okay, look at this. This is the original impact. When we talk about aviation impact, it's very unfair to look at the global average because aviation impacts could be so localized. When you do a global average, you're averaging out regions like this. No. The local impact could be up to 2 watts per meter square. So the global average is very, very misleading when it comes to aviation impact.
The improvement of this MGO simulation done by the unit count is quite impressive.
Yes.
Yeah, do you have any idea what cost that by comparing between the CUP and the unit count?
I've lost contact with Samsu for about a year and a half, so I don't know. But based on my last recollection, it doesn't seem to be a burden on the model simulation. So.
I think, what's your comment on what's the mechanism? I think at least part of it is the explanation that I heard is that Sung-Soo has developed a representation for cold pool triggers. And so, he has an evolution equation for that captures the characteristics of convection and occurring at prior times. So it's essentially a memory for convection, and it's manifested through the evolution equation for the cold pool. And I think that's what helps allow for the future property.
I have his full presentation at Breckenridge in June. If you're interested, I can pass it along to you. He has the full presentation on Unicom in June. Yeah.
Short question. Your treatment of contrail, do you have to deal with the size, dimensions, and lifetimes? How do you do that?
The parameterization assumes that we just assume the initial volume of the contrails. It's somewhat arbitrary. We assume the width and the height being 300 meters. And all the water vapor above ice saturation will be taken into contrails instantly. And then after that, the cloud will be treated basically the same as cirrus. It will just evolve based on the model state. Just like, basically, during the simulation, we can't tell if that's contrail or cirrus. So our baseline is the simulation without aviation emissions, and we just take the difference. So it's not a very detailed model. In ECM 5, I believe, in DLR in Germany, they have a very detailed contrail model, and they can actually pick out contrails with different lifetimes. But I talked to them, but they say they spend, close to 10 years to develop that model, so.
I think we can stop here and then let's thank Dr. Chen again.